algebraic version. So a list of n non-zero complex numbers under coordinate multiplication. And so cohomology in general is a recipe that takes a topological space and produces, or topological spaces, and produces rings, not just any old rings, but graded rings that are super commutative, that the even parts commute with everything, and the odd parts anti-commute with the odd parts. And it's the one thing that's maybe a little tricky about it, well, many things, but one thing is that this upper stars indicate that this is not a covariant but a contravariant functor. So if I have a function from one topological space to another, then it should produce a pullback map from the cohomology of the target guy to the cohomology of the source guy. So every space gets a cohomology ring, and every continuous map gets a pullback map on cohomology. The basic thing one could do so two basic things you can think about when you've got this story are, you can think about X mapping to a point, and that would say that you've got a map from the cohomology of your point to the cohomology of your space. That's not very interesting since the cohomology of your point is just Z, and these are rings with units, so you already know what Z is going to do. The other is that you've got the diagonal inclusion of X into X cross X diagonally, and that gives you a map from cohomology of X cross X to the cohomology of X, and this is really why cohomology is a ring. Okay, so I want to do T equivariant. I won't use this light color. I want to do the T equivariant version of this. So that's going to mean I'm going to have a different black pen, and so I'm going to have topological spaces with a Tn action on them, and I'll put a T here to okay, I'm just going to write T. The N was to indicate the dimension, not to indicate that I'm starting with something one dimensional and taking in power. So that's what it means here, and that's not what it means there. Okay, so I'm thinking of topological spaces with a torus action. I have a favorite one in a moment, the Grassmannian, that we'll get into. And associated to each one of those, I want to associate some ring, and I want this story to continue. If I have now, this should be an equivariant map. Then here, I should get a map backwards on equivariant cohomology. So what you usually do with cohomology rings is you might say I've got X and Y living inside M cycles, and then I can talk about X and Y giving me elements in the cohomology of M. I'll be putting a T on this in a moment, but I don't need it yet. And so let me say these are nice enough cycles in order for this to happen. So the case that's going to matter to us is this will be a manifold, and these will be complex algebraic, complex manifold, compact, and these will be complex subvarieties, and that's enough to be able to associate classes. But what's the ring structure about? Why do I multiply things? This is supposed to measure somehow. This is again some element in the cohomology, and this measures the inability to make X and Y disjoint. So maybe a first example of this is we have a torus. So here's a torus. I've identified these sides and those sides to get myself the torus. And I think about X is this curve on the torus, and Y is this curve on the torus. And you can wiggle them all you want, but they'll always intersect in an odd number of points, or maybe tangentially at a 0 or 2. And so you won't be able to get to intersect in no points. And the product here will be one point. So I want a t-equivariant version of this idea that I'm measuring the inability to make two things disjoint. So in particular, let's take the origin living inside Cn. I did it again. Let's take the origin living inside Cn. Cm, some representation of my torus. And this is a nice torus equivariant map, so I should be getting the origin defining some element of the equivariant cohomology of Cm. So to be clear, I've not defined this functor, and I'm not really, I will give you a definition of it in a moment, but I want you to give the feel for it first, before giving you the rather unsatisfying and pleasant definition that really only a Hawatapi theorist could love. So here I've got the origin inside my space, and I'm going to try and move it away from itself. And if we were doing ordinary cohomology, you'd say, I got this point, let's move it away, and the product will be 0. Not that 0, it'll be the intersection will be the empty set, giving me the class 0 in cohomology. Okay? But now that I've turned on this torus equivariance, there may be no other points inside Cm that are invariant under the torus action. So I try to move it, and there's no place nearby that it can safely go. There isn't going to be a one-parameter deformation of places for it to be. So that's going to happen exactly if the weights of the torus action on Cn, so this guy as a representation, is a direct sum of one-dimensional representations. I'll call them C lambda I. So where the lambda i's are living inside T dual. This is my notation for, the lambda i's are living inside T dual, which I define as from T things. So I can break this guy up into one-dimensional representations, and the question of whether I could get this disjoint from itself is exactly whether one of those lambda i's is 0. So let's say I can't. Let's say I've tried to get it apart and it's stuck, and then I say, well, the intersection, this is as good as I can do, the intersection is that point. Now if I said this, that wouldn't be good from a degree point of view, that the codimension of 0 in here is m, so it should be defining a class in 2m degree, and in degree 2m. This guy should be defining a class now apparently in degree 4m. So to give a homogeneous statement, I need something up front, and it's going to be the product of the lambda i's. I equals 1 to m. So this is the sort of calculation we do in equivariant cohomology. This thing will be 0. This whole thing will be 0 exactly if one of those lambda i's is 0, which is what I wanted. It's measuring whether or not I can get this point disjoint from itself. All right, so now let me give you an actual definition, which is I take, so H star Tn equivariant cohomology of some space M is defined as you take M and you multiply it by the space called Et. I'll define just a moment. Divide that by T, and then compute the ordinary cohomology of that. So what Et is, it's the product of n copies of C infinity minus the origin. So what's nice about this space, why this is a worthwhile space to bring into the story, is so this guy has a free, or let me say just one factor here. This guy has a free cross action, and it's contractible. These are the two desirable properties this thing has. So you'd feel like multiplying by something contractible that shouldn't affect cohomology. So why is it contractible? Well, what's its 5th homotopy group? What's its 100th homotopy group? Right? This is if I took C10 and ripped the origin out, you'd say all the pi i's vanish until pi 19. But now I go to C infinity and all the pi i's vanish, and that's good enough. So it's contractible. That says multiplying by it shouldn't really be affecting things, but it does because now the action on this product is free, and so it's reasonable to divide by it. And so this is the definition. The thing that's really unpleasant about this definition is that this is infinite dimensional, and so one's leaving algebraic geometry in this point of view. But anyway, I'm not going to use this definition any further. I just wanted to admit there is a definition. Really what I want is some properties. And so one thing about this definition is h. So if I compute ht of a point, and actually I'm not going to write this of a point after this point, I'll just write h star t. So that's going to be the cohomology of et divided by t. So that's n copies of Cp infinity, nth power, and that's a polynomial ring in n variables, all of degree 2. So if I just have a single Cp infinity, then the cohomology ring of Cp infinity is a polynomial ring in one variable. Because I'm taking an n-fold product, I get a tensor product of those rings. So that's huge. It's much bigger than the ordinary cohomology of a point was. And that's great because it means that this map could be interesting. It could be that when you take a point and when you map from your space to a point, you find out that your space's T-equilibrium cohomology is a module over this thing. So there's a bit of the cart before the horse here, but I'm going to say these are not just rings, but these are H star T algebras. So let me give a slightly more natural way of saying this, less coordinatized, and I'm going to go back and forth between wanting to do it with or without coordinates. So the most natural way to think of this is that this is the symmetric algebra on the weight lattice of T. So how do you remember that it's the symmetric algebra on that lattice instead of the dual lattice, right? What's a mnemonic to not make that mistake? I want a recipe that takes an element of T dual, so a weight, a representation of T, and produces a cohomology class here, and that will end up being in degree 2. So the natural way you end up with cohomology classes of degree 2 on a space is to take the first Chern class of a line bundle. So what would a line bundle over a point look like? Well, over a point, a line bundle is just, I've got a line, except for the T equivariance. So it's not just a line, it's a one-dimensional representation of T. So the recipe is, you start with a weight, you make a one-dimensional representation, you call it the T equivariant line bundle over the point, and you take its first Chern class. And that gets you an element in H2T. So that's a map from T dual to, so I'm saying H2T of a point. I did it again. Without the point, H2T is just T dual, and then there's no other relations. The whole H star T is the symmetric algebra on that class. So let's, I want to show you how to draw pictures to do calculations in equivariant cohomology. And I'm going to need two results. So one is this, probably going to be invisible colors. One is this theorem, and let me attribute it to Kerwan. It's not exactly the situation she proved it in, but it's good enough for me. If T acts on M, and M lives inside projective space, and it's smooth and complex, so this is a algebraic embedding, then when you think about the so then the inclusion of the T fixed points into M induces an inclusion. This is the interesting bit. So this is stupid. Okay? I've just got a subset. The fact that this is an inclusion is what's interesting. That the equivalent cohomology of M includes into the equivalent cohomology of the fixed points. So this seems like a weird thing to talk about. I have a space. So okay, so this is a space with a trivial torus action, including to a space with an interesting torus action. And the inclusion map is T equivariant. Here, I've got a space with a trivial torus action, and I'm computing its T equivariant cohomology. What would that be? So I look at this again. I say I've got M cross BT over T, and I want to divide by the T. Well, it's just dividing here. The T wasn't acting trivially on M. So I just get the cohomology of M tensor the H star T. So as an algebra, this is just the cohomology, is just H star T tensor over Z with the cohomology of M.
T.
T.
You're converted with the post converted, right?
Huh? Oh, yeah, thanks. Close.
Does the T actually need to extend to CPN?
You can make it do so. So I, sure. So if you have somebody normal with a T equivariant ample-line bundle on it, sorry. You might have to change the projective embedding. So into the original CPN, maybe not, but into some other CPN, yes. But so if I insisted that this be a T equivariant map, it wouldn't get me any more or fewer examples of what I want.
For the Grassmannian, we have a T fixed point in every cell.
Yes. So this is maybe a lot smaller than H star, or at least easier to compute than H star M was. Right? The topology of MT might be a lot simpler than the topology of M. So the case that we're going to focus on in just a moment, in the Grassmannian, the T fixed points of the torus acting in the Grassmannian are isolated. So this is just a finite set of points. And let me say this. If MT is finite, then we continue this and say we're just getting a direct sum over MT copies of this polynomial ring. Yes?
So ordinary cohomology is a functor, right? So if the space has a T action, so this is cohomology. What's the relationship between the equivariant structure and the ordinary cohomology of a T space and the equivariant cohomology?
So there's always a forgetful map from the T equivariant cohomology to the ordinary cohomology. And so where that's coming from is, so I had this, so if this is your definition, as is the only definition we're going to use, I've got my space M cross ET over T, and that has this map. Oops, I wanted this high. And, so I got M cross ET over T, going down to ET over T, and living, so this thing is an M bundle. So in general, ET is a T bundle over ET mod T. So this guy has a name also, which is a BT. So ET is a T bundle over BT. What this construction does, it replaces every T fiber by a copy of M. It's the associated bundle construction. So now every fiber here is a copy of M. Okay, let's take a point living inside here and take the fiber M. And so I get a map from this, so just this is all ordinary stuff. The T action has been eaten by taking this quotient. So don't think about T equivariance here anymore. This is just spaces. This guy's including into here, and so therefore there's a map from ordinary cohomology of this to ordinary cohomology of that. Now, this guy, you can say better. Which is, so I'm going from the equivariant cohomology of M, and I'm going to the ordinary cohomology. That's this. That's what's happening on the stop fiber. Into here, I've got the equivariant cohomology of a point, and by the time it gets to here, I know that everything in positive degree has died. So the map from here to here, from cohomology of CP infinity to some power to cohomology of a point, is killing everything. Is killing all the y's. Now erased. All the generators are in positive degree. So therefore, this map, you could think of it as factoring through this. So you can get a hold of the cohomology of your space by starting with the equivariant cohomology and saying, let's kill all of the y's. And what's not clear is whether that map will be onto, but for these spaces, and if you work over the rationals, it will be. So actually it'll be an isomorphism. You can get the ordinary cohomology rationally from the equivariant, and then setting the y's equal to 0. So we'll do an example of that in a minute. Okay, so I'd like to do a calculation in T equivariant cohomology of CP2. And I need one more ingredient, which is, so if T acts on, and now I will insist that that this is a T equivariant conclusion, so I want this to be the projectivization of some representation I equals 1 up to n plus 1 apparently. Oh, this n is not the same as any other n, so let's make it n. N plus 1 of some representation. Then I want to define the moment polytope of M is the, let me assume this guy is irreducible, is the convex hull of, I take the points, the T fixed points. So for each T fixed point, I can take the line bundle over over CPM, and I can restrict it to that point. So I've got the line bundle that lives on projective space. I restrict it to this point. Now it's just a line. Because this point was fixed, I can talk about how the torus is acting on that line, and I want to take the weight of that. And so this guy is going to be a weight. So each fixed point is going to get me a weight, and then those will all live in the weight lattice, and then I'll take the convex hull and I'll get a polytope. As a variety, so connected, if it's a submanifold being connected. If it's not connected, for example, if this guy were 2 points, then I would want the moment polytope to be those 2 points, not the line connecting them. So, so I'm skipping out on stupid issues there by just assuming this. Okay. So, in inside this convex hole, there's various points that I actually especially care about, like the vertices and whatever other points arose. So I've got this map from the fixed point set to this polytope, and some things go to the vertices and some things go to the interiors. Okay, so now I'm going to draw some equivariant cohomology classes on CP2. So example, let's let T2 act on CP2, and I want the weights to be 0, 0, and 1, 0, and 1, 1. And so then, so CP2 is the projectivization of the three-dimensional representation made of these three weights. So these are elements in my weight lattice. So here's that convex hull, and so this convex hull lives inside T dual, or maybe lives inside that tensor the reals. If you want to actually connect these up, T dual itself is only an integer lattice. Let's consider the class of CP1, and I want to be more specific. Let's take the CP1. Okay, let's consider all vectors that form 0, star, star. So they use the second and third coordinates. This is a CP1's worth of points inside CP2. And I want to consider this guy's class inside the T equivariant cohomology of CP2. So how do you think about it giving you a class? Well, if you have n inside M, then you do this thing to it, and now you have n cross Et over T living inside M cross Et over T. And its codimension will still be complex codimension 1. It'll still be finite codimension, and so you can still assign a cohomology class to it. I'm going to take this guy and restrict this class. I'll follow this map, restrict it to my three fixed points. And what will I get? So if I restrict this to, okay, let me give you an interpretation of this restriction. So I've got some point F living inside the fixed points, living inside the manifold, and I've got alpha, an element in the T equivariant cohomology manifold, and I can ask what happens when I restrict it to this point. Right? This is a T equivariant map, therefore there's a map backwards on T equivariant cohomology. It's going from cohomology M to cohomology of a point. So let me denote this as alpha restricted to the point F, living inside here. And one way to get a hold of this alpha restricted to the point F is to take alpha, multiply it by the class of the point F, and then integrate it over the manifold. So what's integration? Integration is about push forward to a point. I've got a map from M to a point, and I push forward this thing along along that map, and I get a different way of thinking about this element H star T. So we thought about products like this at the very beginning and said they're about the difficulty, like maybe alpha is the class of some subvariety like the CP1. Then this product is about the difficulty of getting this point off of that subvariety. All right, let me finish this picture. So I have the CP1. The CP1 itself is connecting up the 1, 0 and the 1, 1 points. So there's the CP1 I'm thinking about. So I ask, how difficult is it to get this point off of that CP1? Well, it's not even on it, so that's not a problem. How difficult is it to get this point off of that CP1? Well, if I moved it along the CP1, that wouldn't help. So I'm trying to move it in this direction towards the origin. And so I'm measuring remember the calculation we did here was we looked at all of the weights of the of the torus action and multiply them together. Here, what I want is the weights just on the normal bundle. So not the tangent bundle to the CP1, just the normal directions. And I get this weight, so I'm supposed to get some element of H2T, because my CP1 is complex codimension 1, it's defining an element H2. I'm supposed to get an element H2T. H2T is, it was here. H2T is T dual, it's the weight lattice. So this picture that I'm drawing, this multiple polytope I'm drawing inside the weight lattice, that's also where these, that's also where these weights live. So I'm going to draw this and say this is an element of H2T because it's in this picture. It's measuring the difference from here to there. This is what's difficult about getting this point off that this vector is not 0. And similarly here. These three things I've written down are this and this and this are three elements in H2T. So now let's compute. What happens when I take this class, CP1, and I square it? So that, I'm going to take this thing, 0 here, this here, and I square it. Now, thankfully, this restriction map to fixed points is a ring homomorphism. So I can restrict my points and then do my multiplications just at one point at a time. So I just need to, at this point, multiply 0 by 0, at this point, multiply down by down, and at this point, multiply left by left. All right, so I'm going to re-express this mysterious class I have, that's not the class of a subvariety anymore, as a linear combination of classes of subvarieties. It's going to be the thing I started with, times down. So this is also an element in H2T. I could write these guys as, y1 minus y2, things like that, but this is more fun. So I've got so this times that is getting me this. This times that is getting me this, but this times that is not getting me that. There's one more term I need, and it looks like this. Where what I have here is the product of both of these. So what is that thing? This is the class of that point. Which point was it? 1, 0, my second coordinate. So this is the class of just this projected point inside my CP2. So again, how do I know that I'm getting the product of these two lines coming out of here? So this is about what happens when I take the class of a point and I restrict it to that point. Well, that's like taking that point and trying to square it. And so that's what we were doing here. So locally, CP2 nearby that point just looks like C2 when we're back in this calculation of multiplying the weights on that C2. And the weights on that C2 are exactly these differences. So if you think about, if you take an open set on CPN, and you say I'm going to invert one of my coordinates and be able to talk about the other coordinates, inverting that coordinate is looking at ratios. It's going to be looking at differences of the weights. So that's why the weight in this tangent direction will be the difference of these two weights. That's why I'm getting this arrow in that direction. So here I have an equation in equivariant cohomology of CP2. It says if you take this particular line that I had before, so I'm saying CP1, but I mean this specific CP1. So I guess I should say it specifically. If you take this specific CP1 and you square it, you get this equivariant number times this specific CP1 plus 1 times this specific CP0. Okay, so the non-equivariant version of it would be to take this equation, do this tensoring where we set all equivariant numbers of degree more than 0 to 0, we kill those. We would kill this term, and we would find out that if you intersect two lines in the plane, you get 1 point. That's the non-equivariant statement. Any questions right now before we get to the corresponding? Yes.
Can you say again why you squiggled out the diagonal in that triangle?
So this diagonal is the moment polytope for that CP1 living inside CP2. So I can do, if I have X inside M, I can apply that same recipe, and it will be a convex hull of fewer things.
Okay.
So here's the convex hull of those two guys. Yeah.
Could you explain how that linear combination gives the two arrows going left that we needed?
Yeah, so really not sure which is which. Let me put them right side. Good. Okay. So if I just look at the bottom right corner, I'm supposed to be getting this squared is equal to this times that plus this times that, right? So that's the equation I'm claiming. So I claim this, and let me divide everything by this linear factor, and now I'm getting the statement that left is equal to down plus northwest. Okay. And again, all these could be done. These things be. I could say that my T-equivariant cohomology is z bracket xy, and so here I would have minus x and minus y and y minus x. But I do it that way. All right, so let's take T acting on G mod P, and so G mod P could be, for example, GLN mod V, which is flags V1 inside V2, inside Vn is Cn, or it could be GLN mod lock upper triangular matrices, Kn minus K here, and this is the Riemannian of K planes and Cn, or it could be a bunch of other things, but let's think primarily about those two examples. And let me give you a recipe. What if X lives inside G mod P, and I want this map, this